friends, our next topic is topic number 21. It's a potential energy of electric dipole in a uniform electric field. So just know about what is a potential energy. Okay, so first of all, to know about the potential energy we can make a electric field. So these are the uniform electric field. Okay, so this is a uniform electric field. In this uniform electric field, we place a charge. We put an equal and opposite charge at some angle of theta with electric field lines. Okay, this is a negative charge and this is a positive charge with respect to some angle of theta. Okay, so we put in this equal and opposite charges of some angle of theta with this uniform electric field or uniform electric lines. Okay, now what? The electric field are always directed to on that direction, but the direction of electric field moment is going from negative to positive. This is a direction of electric field from negative charge to positive charge. Okay, so now when we place electric dipole in an electric field, what I'm saying to you, okay, just understand. Okay, now when we place a electric dipole in a electric field, in a uniform electric field, the electric field experiences a torque. Okay, so what happened? The electric field, the electric dipole experiences a torque. And what is a torque? Torque is a may I explain you? Okay, then electric field is always directed. So the electric field is always directed to align, okay, align the electric dipole along it. What? The electric field is always try to direct a line of electric dipole around it. So it will make to try to align the same as the electric field. The electric field is always try to align to the electric dipole in a line of the electric field. Okay, now the rotate this dipole. Now we have to rotate. Now from the figure we have to rotate this electric dipole by this. Okay, now rotate the electric dipole for a small angle of d theta in opposite direction. So we have to applying some force to rotate the electric dipole for a very small angle of d theta. Okay, in the opposite direction it will get the position. Okay, now so calculate. So what happened? Understand? So we have to just give the force of electric dipole in a anti-clockwise direction. Okay, now so what? So it experiences a force, okay, in opposite direction of the electric field. So it experiences the dipole, then the electric dipole is experiences a torque and it's work done. Okay, so the work done, so calculate what the work done is corresponding to that force. For the work done, this experiences first a torque. So torque, the equation of torque is P into E, where the P is electric dipole moment and E is electric field, okay, in form of the vector. But in form of the magnitude, when the cross product is removed, then we have to put here a PE into sine angle, the sine theta in the magnitude form. Okay, this torque will try to align. Okay, so this torque is try to align the direction of in an electric field. Okay, understand what I am telling to you? When we have to put a dipole in a uniform electric field, it experiences torque. Okay, so and we have to applying the opposite force to this dipole. Okay, so this dipole, the work done is by the external force. Okay, so when we have to applying the opposite force, we have to applying the external force. So the work done is experienced by this is external force. So the work done W equal to, what is the equation of work done? Work done is a force into displacement. Okay, so here a force is a torque. Okay, so torque into displacement. Displacement is a small angle of theta is a d theta. Okay, so now, but we know that our work done of the electric field is opposite to the work done of external force. Okay, so the work done of external force is opposite to the work done of electric field. Okay, so we have to say that work done by the electric field is, so work done by the electric field is positive tau into d theta. Okay, but in our case, it is a small change of the work done with respect to the small angle of d theta. So the small work done with small angle dw equal to minus pe sine theta into d theta. Okay, now for the conservation of the force, okay, for the conservation of the force, the change of work done, okay, so the change of work done is equal to the change of the, it is equal to the negative sign of the change of the potential energy. Once again, the work done must be equal and opposite to the potential energy of the dipole. Okay, so it's a delta W equal to minus of delta U. Barabar, okay. Now, so the du equal to minus dw. Okay, the du equal to the minus minus, we can get a positive pe sine theta into d theta. Okay, now for this figure, the total energy stored into the electric dipole. So the total energy stored in the electric dipole, the total potential energy equal to U equal to close integral of the du, the all amount of potential energy. Okay, so is integration from the theta 1 to theta 2. Theta 1 is the initial angle of dipole, theta 2 is a final or a second angle of the dipole. Its equation, and the du is p sine theta into d theta. So p is a constant, we can make out. So p is a theta 1 to theta 2 sine theta into d theta. And what is the integration of the sine theta? It is a minus cos theta. Just put here theta 2 in place of the theta, minus in place of the theta, theta into minus of cos theta 1, minus minus plus. So the equation of the total potential energy, U, the total potential energy equal to P into E. It's not a potential energy, it's a dipole moment with electric field in bracket minus cos theta 2 minus minus plus cos theta 1. Where theta 1 is indicating here angle of initial angle of dipole and theta 2 is indicating the final angle of dipole. Okay, now so when theta 1 is the initial angle of the dipole, so it is like the reference. So when it is in the initial angle of the dipole and it is in reference, the potential energy is 0. Okay, so when the potential is 0, the theta is must be pi by 2, because when cos when in place of this equation we have to put here a cos 0. Okay, so the 0 value of the cos is 1, so we can make here a pi by 2, 90. Okay, so for the initial condition, theta 1 equal to pi by 2 and the potential is a 0. Okay, now for the theta 2, the angle is must be any of the angle of theta. Okay, so for the general expression of the potential energy, U equal to minus Pe cos theta, and we can also in a vector form, it's a minus P the dot product of the electric field. Okay, so electric moment is a so the electric potential, the general expression of the potential energy U equal to minus P into E cos theta, and we can also in form of the vector form, it's a minus vector of dipole moment to dot product of electric field. Okay, now I hope you enjoy this session. Thank you.